Okay, so I will repeat now. It's my pleasure to announce a talk by Yacine Barhoumi-Andréani. The title is A New Approach to the Characteristic Polynomial of a Random Unitary Matrix. Please. Yeah.
Yes, thank you very much for this invitation. This is a great pleasure to be virtually in Sofia. So this is a talk which is based on the following paper, which is on arXiv. And this is about the links between the characteristic polynomial of a random unitary matrix and number theory, because the motivations of this particular field find its roots in number theory. So the first part of the talk will be general reminders or a general story that you might not know about the links between random matrix theory, random unitary matrix theory, and number theory. So I will explain you the so-called Montgommery-Dyson correspondence. And then I will explain you some of the latest developments in the last 20 years, notably the moments conjecture of Keating-Snaith. Then I will explain you what we compute in this theory, so the functionals of interests and what kind of results we aim to have. And then finally, I will explain you on one particular example, my personal contribution. So this is this big paper that I mentioned. This is slightly big, so I will give you one example, and then you can check the other theory if you want. And then finally, I will be very fast on the proofs, and I will give you some comparison with with one of the main techniques of the field, which is called the CFKRS approach. Okay, so the motivation starts with number theory, and the only thing we really need is the definition of the Riemann Zeta function. So you have this sum, the Dirichlet series, or the Eulerian product. So this is the product which is the most interesting part here. So of course you can extend it to the complex plane. And there is the famous Riemann hypothesis that states that the non-trivial zeros are of real part equal to 1/2. So the zeros are sigma k plus I gamma k. I will use this gamma k notation. So you can do a statistical study of the zeros of the zeta function. And this was originally done by Montgomery in 72. So you see, you take the zeros. You don't necessarily suppose that the real part is 1/2, and you rescale them with a particular function, with the function x log x. And by doing so, you have the order between the two zeros is of order 1. And you see, you compute the following quantity of the zero. You take a function phi, which is C infinite with with the support of the Fourier transform, which is between -1 and 1. And you compute this quantity, which is called the pair correlation. So this is phi of gamma k minus gamma L. And you see that when you rescale, you tend to, at the limit, to a particular functional, which uses this function, the function 1 minus sinc square. So the sinc function is an important player in this talk. This is the function sine x over x. This is something that comes back often. So this is a theorem because what Montgomery managed to achieve is to relate this sum with the sum over primes. And he had to compute, let's say, pair correlations between primes. Sorry. So if you, and because of that, you needed to control sums of couples of primes. And but if you want to extend the support of the Fourier transform outside -1, 1, Then you need a quantitative version of the twin primes conjecture, and this time it's a conjecture. So it's this is related with the method of computation. Okay, so now the link with random unitary matrices. So before explaining you this link, I need to explain you the model of random matrices. So the random matrices that we consider as are the Haar-distributed random matrices. So namely the uniform distribution on the space of unitary matrices. So this is called the circular unitary ensemble in probability theory, the CUE. And the way you compute is you use this theorem of Weil in the 30s that gives you you see, if you want to compute, let's say, a functional which is invariant by conjugacy, so this is a class function, which is integrable, what you do is a disintegration of the measure with respect to the map of diagonalization. So you can disintegrate the measure, the Haar measure of the unitary group with respect to this map. And you find, if you compute the Jacobian of the map, the complex Jacobian, namely you have to take the square, you find this function, which is the square modulus of the van der Monde determinant, you see? So for the physicists who are in the talks, you should understand that as a Coulomb gas, if you take the exponential of the log of this thing, you have the log of exponential I theta L minus exponential I theta K. So you have the log of xi minus xj at inverse temperature 2. So this is a Coulomb gas. So this is a particular type of integrable system, which is related with Calogero-Moser, for instance. But this is not exactly this because you are on the circle here. You are on the unit circle. So you have this theorem. So you can compute more or less everything which is invariant by conjugacy using this formula. And you can, in particular, compute the equivalent of the pair correlation of the zeta function, zeros, with the eigenangles of the random matrix. So you see, you do the same as before. You make a little transformation that transforms the eigenangles to be of order 1. So here you just multiply by n, and you compute the same quantity. And you see that the Montgomery theorem was from 72, and the Dyson theorem is from 62. So it was 10 years before Montgomery. And you find exactly the same quantity. This is this 1 minus sinc of pi x squared. So here there is a mystery. You see, if you find the same thing, this means that there is something behind. So this is the Dyson-Montgomery correspondence. There is a famous story that they met during an afternoon tea, etc., and then realized that they were computing the same thing and that they had the same result. But so this is the history. You have I give you a few dates. So you see that 62, this is the Dyson theorem, 72 Montgomery, 73 they both meet and they realize that there is a correspondence between the zeros of the zeta function and the eigenangles or eigenvalues of the random unitary matrix. In the 80s and 90s, there was not so much that was done. There were numerics and conjectures, but not so much. In 99, Katz and Sarnak proved the analog of the Montgomery conjectures over finite fields. So this is something that you can do if you don't understand number fields, namely the zeta function. You can go over finite fields where you can define equivalence of zeta functions, where everything is more or less proven. So, for instance, the Riemann hypothesis was proven by Deligne. You have the Hilbert-Polya conjecture that says that the Riemann zeta function would be the characteristic polynomial of some operator. This was proven by Grothendieck over finite fields. So you can do computations over finite fields. This is what Katz and Sarnak did in 99. In 2000, this is one of the key papers of the theory. This is the paper by Keating-Snaith that used finally this Montgommery-Dyson correspondence to make a conjecture about the moments of the zeta function. I will explain that in a few minutes. And then in 2003, there is what I call the CFKRS formula for Conry, Farmer, Keating, Rubinstein, and Snaith, which is the main way people compute in this theory. Okay, so now what is this paper by Keating and Snaith? So you see, you can make the probabilistic study of the zeta function. This is not the same as the study of the zeros. Here, what you do is you randomize the zeta function. So you take a uniform random variable between 0, 1, for instance, and you take the value of the zeta function on the line real part equals to alpha, and in a random point of this line. And then you have a parameter t that tends to infinity, that becomes big. And you see that there is something that happens if you do so. The primes in the product, the prime factors in the zeta function products become independent. And you have to take alpha bigger than 1/2. Here, and not alpha bigger than 1. In fact, this product is defined inside the critical strip for reasons of probability, because the variance of this term is finite. So because of the randomness, you win something compared to the non-random zeta function. But yeah, so you have a particular distribution, which is called the Bohr-Jessen distribution. This was done by Bohr and Jessen in the 30s. But now this is only for alpha bigger than 1/2. If you want 1/2, then this product diverges. And so you need to renormalize. Namely, this was done by Selberg in the 50s. So what you do is you take the log and you divide by the variance, which is in fact log t. And what you find is the Gaussian. So this is a famous theorem of Selberg that he did not publish. And in fact, he did not realize that it was the Gaussian that he had. But anyway, so once you have the fluctuations, so this is a central limit theorem. So you have the convergence in law or convergence in distribution. So what you want to do in a probabilistic study is the next step, which is called the large deviations or the precise large deviations or the mode Gaussian convergence. Mode Gaussian convergence is a concept introduced by Kowalski, Nikekbali, and Jacot that formalizes this type of computation. So what you do is you compute the Laplace transform of the random variable. So the expectation of the exponential of lambda times the random variable. And you look at its behavior. So you see exponential lambda 2 over 2 times 1/2 of log t. This is the Gaussian. So this is 1/2 of log t times this Gaussian. But then if you compute precisely, what you have is a correction. You see. So this result is only proven for lambda equals 2 and 4, which means this is the moments of the zeta function in this uniform, this randomized zeta function. So lambda equals 2, this is Hardy and Littlewood. Lambda equals 4, this is Ingham. You have a conjecture for lambda equals 6 and 8 by Conry-Gauche and Conry-Gonek. And so far, this is purely conjectural. This result is a general conjecture by Keating and Snaith. And so you see, you have two terms at the limit. So you have phi a, which is called the arithmetic factor. So this is a bunch of product of two F1 functions. And in fact, this is the renormalized Laplace transform of the Bohr-Jessen random variable in 1/2. You see, if you need to have a correction in exponential minus lambda 2 over p. But otherwise, this is the Laplace transform of this Bohr-Jessen random variable. You see, you have p power alpha for alpha equals to 1/2. And then you have a correction. And this is the correction that no one was able to find. So the correction looks like a little the arithmetic factor. It's a product of 2f1. It has a more famous form using the Barnes double gamma function. And this is what Keating and Snaith managed to find. So how did they do? If you remember the Selberg central limit theorem, the question is there something that looks like the zeta function that would satisfy the same? And if you remember the Montgommery-Dyson correspondence, if the zeros of the zeta function look like the zeros of a random unitary matrix, then the product over the zeros, namely the characteristic polynomial, should look like the zeta function. So this is the idea that the characteristic polynomial is a toy model for the zeta function. So what plays the role of the critical axis 1/2 is the value in 1, because 1 is the critical circle, let's say, for the characteristic polynomial. You have a functional equation that uses the unit circle as a reflection. And in fact, you can compute that the log of the characteristic polynomial satisfies the same type of central limit theorem. So what Keating and Snaith did was to compute the Laplace transform of the log. They could do it with general formula. And they found a factor, this one, the matrix factor. And then the variance is log n. Previously, the variance was log t. So they make the association n equals log t, and they produce the conjecture. So you see, this is a general philosophy. So either you can take a problem which is already solved in number theory, and you can adapt it in random matrix theory. So for instance, the Selberg CLT was proven. You can go to random matrix theory to see if you have the analog on the characteristic polynomial. So this is the Keating-Snaith CLT. But this is much more interesting to take an unsolved problem on zeta, namely the moments, to find the equivalent problem on the characteristic polynomial, to compute, because you can compute on the unitary group, and then to come back and say, look, there is a correction that comes from random matrix theory. So there is a universal term which concerns the roots of the zeta function and the eigenvalues of the unitary matrix. And this is universal. So this is this Keating-Snaith philosophy. And this is interesting because you can compute on the unitary group. And how can you compute? Well, you have a lot of techniques for that. For instance, you can this formula of Weil of integration can be related with Toeplitz and Fredholm determinants. This is a very simple manipulation. So you can express functionals as Toeplitz or Fredholm determinants. You can use orthogonal polynomials on the unit circle exactly for the same reasons, because Toeplitz determinants can be expressed as products of norms of opaques. You can use mathematical physics, supersymmetry, integrable system. This is more or less the same techniques. Algebraic combinatorics, representation theory and symmetric function. So this is where I am more or less. And here also, probability theory. So this CF-KRS formula that I will present at the end. So you have also some determinantal and integrable probability. Weingarten calculus, this is a special type of calculus on the unitary group. Ito calculus, this is classical probabilistic theory. You can define a Brownian motion on the unitary group, etc., etc. So you have plenty of ways to compute, and this is what makes the theory interesting. In fact, I would say, you know, this is a random unitary matrix. This is a little the Swiss knife of it's a theory. It's a Swiss knife theory. Namely, if you know something, you can come to random unitary matrix and apply. Most likely, it will be applied, because you see the range of techniques is very huge. So yeah. Okay, so now I will explain you what kind of things we compute. What are the people interested in? So, for instance, you have seen that we have computed the Laplace transform of the log, namely the moments of the value in one of the characteristic polynomials. So people compute mainly integer moments because they can. And yeah, other functionals are more complicated. So you can compute the joint moments of products or ratio. If you have products, this is called the autocorrelation, and this is an important object. The derivatives, you see, this d over dr is the derivative in one. You can compute the secular coefficient. This is what I will explain in this talk. So secular coefficient is just the coefficient of the expansion in the canonical basis of polynomial, namely x power 1, x squared, etc. Now there is a -1 power j. So sometimes you have functionals that come from finite fields. You see fq of x. This is due to this Katz and Sarnak theorem that in fact explains that if you pass to the limit over q, you get the unitary group. So then you have some functionals of the unitary group. And here this was a link. This was a functional with the number of prime factors of random polynomials over a finite field. You can truncate the characteristic polynomial, and here this is particularly interesting because if you take the equivalent problem on the zeta function, you have the truncated zeta function where you sum the Euler series from 1 to L, let's say. So if you have an Eulerian polynomial, then you can compute. So this is particularly interesting because you have a truncated zeta function. And the last functional, the last trendy functional, let's say, this is the moments of moments. You see, you take the moments of the characteristic polynomial in theta. So this is the moments as a function of theta. And then you take the moments of these random variables. So this is why it's called the moments of moments. And this is related with the maximum. So when beta becomes big, this looks like exponential of the max of the characteristic polynomial, and this is related with the max of the zeta function on the critical axis. So, so this is the kind of functionals that you have. You see that they depend on n. And now the type of result that we ask for is the limiting behavior when n grows. Namely, you want to have, so every time in all the cases that you have something like a coefficient times n power an exponent. And in fact, you see on the, so this is Ks, this is the Keating-Snaith functional, so the moments of the characteristic polynomial in one. You see that you have a coefficient which is this moments conjecture factor, and you have n power k squared. So the power of n gives you the probabilistic behavior, because this is exponential 2 times log n times k squared over 2. So k squared over 2 is the Gaussian, and n, you should understand it as exponential of log n. So this is the variance, or square root of log n. So, so the probabilistic information is in the power of n, and the large deviation should be understood in this coefficient. So this is very important to analyze the coefficient, because this is this coefficient that will tell you what is universal in the zeta function. So you can do it for the autocorrelation, for the derivatives, the mid-secular coefficients, etc., the truncation. So here you can also see something interesting. For instance, if you have the same exponent, so you see this is the mid-secular coefficient, the Fourier coefficient. And here this is the truncated characteristic polynomial inside the unit circle, inside the unit disk. And you see that they have the same exponent. Whereas here, this is k squared, which means this is Gaussian, exactly in the same. So if you truncate the characteristic polynomial in one, it's the same as if you don't truncate, more or less the same, because the functional is not the same. But this is still Gaussian at the first order. Whereas those two, they are not Gaussian. Okay, so now you have seen one example of the limiting functional. The question is what these coefficients look like. And I give you a few examples. So for instance, for the derivatives, this is a paper by Conry, Rubinstein, and Snaith. You see that, so here they have this, what I write as an expectation, they have an integral over un. You see this coefficient bk, this is a sum of derivative of a so-called Hankel determinant, not Toeplitz. Hankel means that you have I plus j. So you see, you have a sum of Taylor coefficients of a Hankel determinant that involves the Bessel function, or you have a sum over partitions of the integer. So here, if the people know, you see that this is the dimension of a module of, because you have the factorial here, this is the module of the symmetric group. So this is related with some measure over partitions. So this is a result of the A. So this is one first example. So I give you a second one. You see that it becomes much, much more involved, because this time for this this functional that comes from the finite fields, you have a sum of GKL, and the GKL are those iterated integrals with van der Monde-like determinants, lots of conditions. And you see that there is this JL, which is one of the main players of the talk. This is an important object. At the end, I will explain what this is. And I give you a last one, the moments of moments. And this time you see that it really grows in complexity, because here you have a bunch of sums in text by lots of. So this is, but this is always the same structure. You see, you have some type of van der Monde terms. You have this psi function that I will explain at the end, etc., etc. So this is very computational, very complicated. And so this is what I will try to, so this is where I come into play, trying to simplify and to reprove of all those results. So I will explain you what I did. So now this is my main contributions that you can find on arXiv. And I will explain that to you on one example. But in fact, I can rederive all the results before and the new ones. So the mid-secular coefficient. So the secular coefficient, I told you, this is the Fourier coefficient, or the coefficients of the characteristic polynomial in the canonical basis, 1x, x squared, etc. Okay, there is a factor -1 power k, but you don't care. So, so the first coefficient is the trace, the last is the determinant, and more generally, the case coefficient is the trace of the iterated wedge. So this is the case elementary symmetric function in the roots of the polynomial. Okay, so this elementary symmetric function, I recall that this is this formula. And there were already several studies concerning this secular coefficients. So the first article was by Hacke, Kuss, Sommers, Schomerus, and Zykowski, and it was related with quantum chaos. So a question of some quantum computations. So then there was, they computed the moments, expectation and variance of the secular coefficients. And then Diaconis and Gambert generalized this to moments. And the moments were involving magic squares. So this is a paper that was considered as very cute, because this was completely unexpected. And there is a last paper that was published exactly at the same time as mine on arXiv, which analyzes the secular coefficient with multiplicative chaos. So this is one of the theories that are developed right now in probability theory. So there is a link with multiplicative chaos. But so what were those people and myself trying to do? So Diaconis and Gamber ask a question about the mid-secular coefficient. Namely, you see this SCK. When you take k that grows with n, for instance, you take integer part of n over 2, Diaconis and Gamber were asking what happens. So they say, on the one hand, the formula linking coefficient and traces of powers, namely, suggests it's a complex sum of weakly dependent random variables, so perhaps normal. On the other hand, the formula expectation 0 and expectation of the square modulus equals to 1 hold for all k, making normality questionable. And so here is a theorem of mine that you can find on arXiv that computes the precise behavior of the moments of the mid-secular coefficient. So I could take rho equals to 1/2, but I take a general rho. And you see that this is n power k minus 1 square, which means that it cannot be Gaussian. Gaussian would be k square or k square minus alpha k, but it cannot be k minus 1 square. So what is this? So you have the behavior, and here, so this is the main interest in my type of results. You see that the result is an integral over r k minus 1. Minus 1 is important here, of a certain function against a square van der Waals determinant. The function writes as a particular exponential that I could put elsewhere, a product of two functions power k, so h rho and h1 minus rho. And this h rho is an integral involving the sinc function, a la Dyson. So this is here, this is something that really looks like the Dyson and Montgomery result. You see that there is the sinc function in this limiting integral, and this is the presence of the zeros. Okay, so now very fast, I will give you 5 slides of an idea of how I get this kind of result. So very, very fast. You see, so I will not kill you with technicalities, but quickly, so you see, you start with a tensorization, namely you write the functional as a linear functional of the characteristic polynomial. So you take the xm Fourier coefficient of zun of x, and you write this as a product over k of each coefficient. So you have xm power 2k, you write x1, x2, x3 until xk, y1, y2, y3 until yk. And then you take out the coefficient and take the expectation of the product. So this is a little Fubini. And so what you want to compute now is a multivariate Fourier coefficient of this expectation of products, which is called the autocorrelation. So I said that this is a universal first step because all the computation start like this. So this is really the beginning. And now you have to analyze this autocorrelation. So you have several formulas for that. So I give you one by Ackman, Vernizzi, or Fyodorov. This is a ratio of determinant divided by a product of two van der Waals determinants. You have lots of other formula, Borodin, Olshansky, Strauss, etc., etc. And this famous CFKRS formula that I will present at the end. But what I will use is the link with representation theory that was done by Bump and Gambert, and that followed the results of Diaconis and Shashahani. So this formula expresses the autocorrelation as a Schur function indexed by a rectangular shape. So Schur function, I recall what this is. This is this function that for instance, this is one formula for the Schur function. There are plenty of others. And the goal is to find a good formula for the Schur function so that you can rescale. And so here is such a formula. So this is my alternative to the CFKRS formula that is used. So you see that I use, so this is an integral over K of a square van der Waals determinant. And here you have a particular function. You have H index n times K of K times L variables, Ti, Uj. So this H function is the so-called complete homogeneous symmetric function. So this is almost the same as the elementary symmetric polynomials, but there is inferior or equal in the sum. And this is the coefficient of this generating series. So I use a little trick which consists in adding 0, because at the end it will be useful. Yeah, if you take the nth Fourier coefficient of this series, multiplying by s to the n plus 1, this means that this is 0. So I am adding 0. This is a little trick. So I will explain where this formula comes from later. So what you do then is, okay, here you have a critical manipulation that explains why everybody gets messy with those computations and why you have very huge computation. In fact, in all those formulas of autocorrelations, the integrand concentrates on the hyperplane. So in fact, you have a loss of dimension in the formula. But in fact, because you have this Hn function that has a scaling property, and because the van der Waals determinant has a scaling property, what you can do is to pass in the projective coordinates. You see, you can divide by one of the coordinates. So you are in the projective space, let's say. And in fact, you see that you can kill one of the variables of integration, because here you have u1 power nk. Here you have k terms of u1 power minus n. And here the square van der Waals, it gives nothing, because you have the modulus of u1, which is on the unit circle. So it's modulus 1. So you see that you can, so you integrate direct 1. So you can kill one variable. And this is the ultimate formula. And you see that you have an integral over k minus 1. If you remember the result, you had an integral over r k minus 1. So this comes from here. So you have lost one dimension. So now, last slide, what do? You take, what you want is to take the Fourier coefficient of S and K of xy. So now you want to rescale with this good formula. So you take xk, which is exponential I theta over n, y, which is exponential I alpha over n, u, which is exponential I phi over n. U is in the formula here of the Schur function. And you rescale everything. So you have this h n rho of exponential I something over n, which gives at the end this product of sine kernel of sinc function. So this is the famous h rho. The van der Waals coefficient you can rescale. And then you have an extra term that becomes 1. So you have this term, power n, but you have divided by n, so it's of order 1. So what you do then is to collect the powers of n to have the right power. And to prove the result, you need some estimates of dominated convergence, etc. So this can be done. So yeah, you see, this is that's the end of the technicalities. So this is what you do. And you see, because of the critical step of concentration, you are able to bypass the complicated sum to massage the autocorrelations that was done in the previous examples that I showed you, all those big sums for the results. Okay, so now for the last part of the talk, I will show you what they are doing in this field. So you see. So how can you understand? So what I'm doing is the following. for those who know symmetric function theory or mathematical physics, I express the Schur function of the diagram k power n, which initially writes as an integral over un with a certain stuff that minus k. So this is a simple manipulation that you can do at the beginning. Namely, you can, you see, if you had the product of characteristic polynomial with a conjugate, you can factor out the determinant and put it here, and then you have everything. Instead of u minus 1, you have the u minus 1 only here. And here you can see that this is a Schur function. And what I do is I switch m and k. And by doing this, I change 1 plus x by 1 over 1 minus x. You see, identity minus tj minus 1. And this is the so-called omega involution in the theory of symmetric function. So what this is called duality in mathematical physics. So you have exchanged n integrals with k, and you have exchanged the ek's with the hk's. So okay, so this is to explain in terms of physics or algebra what is done. So there is one advantage in this formulation. You see that I still did not explain you where it comes from. There is still a manipulation to do. But one advantage is to use an abstract alphabet here. You can do that. I can explain later if you want in the questions what I mean by abstract. Okay, so now where does the S lambda comes from? I mean, where the integral comes from. So here you can understand that with the concept of reproducing kernel and reproducing kernel Hilbert space of symmetric function. So this is an extract of the book of MacDonald, the Symmetric Function and Whole Polynomial. And you see that you can express any function in the space of symmetric function, lambda, as a scalar product against the Cauchy product. So in the symmetric function theory, you can have an infinite number of variables, and this scalar product is the so-called whole scalar product. So this is very simple because this Cauchy product satisfies an identity, the Cauchy identity, that writes it as a sum over Schur function in x times Schur function in y. So as MacDonald says, in other words, C of xy is a reproducing kernel for the scalar product. So you see, if you have a finite number of variables, then you have you can specify you can give a concrete form of the scalar product. And this is one of the key remarks of Diaconis and Shashani. This scalar product is the L2 scalar product of the unitary group for the Haar measure. Namely, this is the scalar product with the square van der Monde determinant if you have class functions that are invariant by conjugation. So you see that writing S lambda of A equals integral of S lambda of u minus 1 times the Cauchy product against this delta of u. This is exactly this formula of reproducing kernel. And if you take lambda equals n to the k, namely the rectangular shape, if you take the length L exactly equal to this k, what you have is the product of ui. So you have the determinant power n. So this formula that I use, a first step in the formula that I use is just the reproducing kernel formula for the unitary group. Okay, now you have the reproducing kernel formula. And what I use is I replace the Cauchy reproducing kernel by something else, by this H lambda. So in fact, there is a general notion of restricted reproducing kernel, but this is a trick. The trick is you can write the Cauchy product as the generating series of a tensor alphabet, so xi, yj, and the generating series of the hn, so this is this h, the Cauchy product, this is the sum of hn of x times y. And in fact, the Cauchy product, this is the Cauchy identity I was mentioning. This is the sum of s mu of x times s mu of y. So this is the famous identity in symmetric function. So you see that if you kick out n, you have hn of xy. This is the sum of s mu of x times s mu of y when the length of the partition is n. So this is this h lambda of u. And why can you kill all the other terms? It's because of orthogonality. If you don't have the same size, you have no chance to be in the sum. So by orthogonality, you can take h lambda. So this is what I use. So, and this is very useful because you can do the rescaling that I did. Everything is polynomial. Now, what are CFKRS doing? So you see, they have also a formula of short function, but this is a very complicated formula. There is a kind of Cauchy product here. This is not a symmetric function because they have a term which is not symmetric. So why do they have this? It's because they start by desymmetrizing a formula of short function. They sum over permutation in a certain subset of the symmetric group that differentiates between the first case coordinate and the last case coordinates. And then they use the reproducing kernel formula. But they use it with 2k variables. You can choose the number of variables, it doesn't change. The minimum number of variables is k, but you can take 2k. So you use the Cauchy reproducing kernel formula. And because the permutations, they disappear, because you integrate over. So you have a combinatorial factor, which is the size of this subset of the symmetric group. And this is how you get this complicated formula. And because you have a lot of drawbacks, you see, you have exponential variables and polynomial variables. You don't see the scaling of the short function. You have etc. You are not polynomial, so you have lots of problems. And this is why you have a gigantic expression to rescale. And at the end, they still end up rescaling this hn function, like I did, but it's hidden in their computation, you see. So they have a bunch of terms like this. So they call it lemma on geometric sum. And in fact, this thing is the rescaling of hn. So this is what I write with the sign kernel, a la Dyson. So here, hidden in this term, you have the sync function of Dyson. Okay, so that's a conclusion. So if you have to remember something of this talk, apart from the history and what we like to compute, this is the fact that the main technique consists in exchanging n integrals with integrals. So this is duality, and you do that with reproducing kernel methodology. Okay, there is an extra way to compute, which is probabilistic by randomization. So this I leave to the people who want to know about it. This is on the paper I mentioned on Archive. And at the limit, yeah, this is something that that I should mention. At the limit, you always have the form a coefficient times n to a power. And the coefficient will always be an integral over r3 minus 1 times a certain functional and the square van der Waals. And this expression with square van der Waals can be written as Hankel determinants. So this solves the conjecture of Keating and Asiotis. He was asking when we have this Hankel determinant. So in my case, you always have Hankel determinants at the limit because you have this stuff. Okay, and so I give you what kind of the functional. So you see, in the case of Keating-Snaith, I can rederive all the functionals. So this is in this paper I mentioned. And so this is the characteristic polynomial in one. This is the mid-secular coefficient I showed you. This is the functional for the that comes from the finite field, the autocorrelation, the derivative, the truncation, etc., the ratios, the moments of moments, etc., etc. So yeah, and I think I can stop here. So thank you very much for your attention.
Okay, let's thank our speaker. Are there questions, comments?
Excuse me, can I ask? My question is follows. You present the new polynomial, or you present the new method of computation of the characteristic polynomial of a random unitary matrix. What is your presentation? Excuse me, it's
Z is the characteristic polynomial of random unitary matrix, you see. So this is, I introduced it here, you see. ZUN is determinant of identity minus Zn of x is identity minus xun. So this is the characteristic polynomial. So this is maybe I should have written it big. So this is all this talk was about this characteristic polynomial. You compute functionals of the characteristic polynomial.
And usually for characteristic polynomials there is variables, lambda and
yes. I take it in one, but yeah, you can put the lambda in front of un.
Thank you.
Yes. Yeah. Did I say that later? Yeah, I did not define, but yeah, because I thought it was. But yes.
May I ask also a question?
Yes, please.
Or make some comments. So first, this duality you're talking, we usually in physics quote level rank duality.
Yes.
It is something that appears in many cases. And my question is about this truncation. So you mentioned truncation of the characteristic polynomial on one side, and also you can regard this problem on a finite field.
Yes.
These are two different directions of generalization, or
yes. Yeah.
So is there some relation between the two?
Well, for the truncation, not that I know, because Katz and Sarnak, they only computed for the exact characteristic polynomial. There are two papers on the truncated characteristic polynomial. This is by Conry and Gambert and by Heap and Lindquist. And what they do is, you see, it's at the end. They do the truncation in one, and they find n power k square, and the other one take the truncation. Okay, inside or outside, there is a lambda minus rho, so this means there is a lambda minus 1. So this is in n k minus 1 square. So this is, and they, in fact, okay, you could have some transition between the two, but so this is only on the characteristic polynomial and the truncated zeta function. But over finite fields, there is almost nothing here, except this. So the characteristic polynomial, this is computed by Katz and Sarnak. But there are, all the rest. And this thing also, because it comes from finite field. Otherwise, they did not compute much over finite fields.
But do you think this is an interesting direction, or
yes,
it should be?
over finite fields, you can compute everything. So this is why it's interesting. In fact, over finite fields, when Q tends to infinity, Q being the characteristic of the field, you should be able to. Normally, there is this Katz and Sarnak theorem that says that you have averaging of monodromy groups. So basically, when Q tends to infinity, you should get the unitary group. So, and this is what they do here. When they make Q tends to infinity and they have a functional over the unitary group. So the finite field case is the toy model of the toy model, where you can again compute everything. And when you pass to the limits on the characteristic of the field, you get random unitary matrices, normally. Well, everything I saw, this was the case. But yeah.
Okay, well, thank you. Thank you for the interesting talk. Talk more.
Questions, comments?
May I ask a question or just make a comment? Thank you for the very nice talk. It was very concentrated, a lot of stuff. I just enjoyed listening at this moment of these functionals, which it's not strange, it's kind of sure functions appear there. See, I didn't see how it develops further. I mean, using some standard approaches in the theory of moments. But I have a question which is not related, I mean, directly to any concrete point here in the talk. So do you know any nice results similar to the random matrix theory in the theory of so-called random tensors?
Ah, yes, I think that it starts being developed right now. So the problem of random tensors, as far as I understood, is that the diagonalization of higher order tensors is not developed. In fact, the people in the 19th century, Sylvester, Cayley, etc., they didn't find a good theory of invariance. And as a result, you cannot talk about eigenvalues and eigenvectors of higher order tensors.
Yes.
So here, this is a very algebraic problem because you can create random tensors and compute a bunch of functionals of the tensors, but you don't have precise invariance like the eigenvalues. So, so the results I saw were about some equivalent of traces of powers, let's say. So they were computed a bunch of powers and they were taking some matrix coefficients. And then, yes, you can have, if you have a tensor of order n, let's say, you can make n tends to infinity and you will have some results, some law of large number, etc. So you have equivalence of results at the beginning of random matrix theory. Let's say.
Yeah.
So,
Yeah, well, okay. It's, I mean, you indicated the most important problems, Sylvester, Cayley, etc. in the 19th century. And now it's very, I mean, especially in numerical analysis, they started considering these canonical forms of tensors. But still, it's an open problem. Yes, eigenvalues, eigenvectors, etc. So well, I just wonder whether it has physical meaning. I mean, in the way of random matrices have that's physical meaning.
Ah, good question. I only saw a few talks about random tensors, so I don't remember exactly the motivations. But yes, you have models of. I'm sure you have models of mathematical physics behind. I don't know exactly which models. Yeah,
the matrices, that's clear. Yeah, we know them. But for random tensors, I just wonder.
I don't know, because those unitary matrices, you see, they have they model quantum gravity, etc. You can couple a bunch of matrices to to model lots of interactions. The tensors, I don't really know. For the motivations, you have to ask true mathematical physicists. Yeah.
True
So-
mathematical physicist is like a good mathematical physicist, maybe.
Yeah, maybe.
Yeah.
You say that.
Okay, thank you.
More questions? Comments? Well, if they're none, then let's thank the speaker again for this very contentful talk.
Sorry, I have a question just in the chat.
Okay.
I asked Yacine, thank you, for a reference of the book you cited, of MacDonald.
Yes.
Yeah, I saw that in the chat, yes.
Yeah.
I don't see the chat.
Okay.
Where is that? Ah, yes.
Yeah, MacDonald has two books,
yes.
and you may find it immediately in the internet.
Yes, this is
Ah,
the book of MacDonald. It's symmetric functions and whole polynomials. This is really the Bible, you know, this is the Bible. And,
okay.
this Cauchy kernel is on page, I think I gave the page because page 68, example 9. You see, MacDonald's book is very, very dense. You have lots of things. So this is a little tiny example, but you understand that better if you read papers of Diaconis and Shashani, etc. But this is in the book of MacDonald, but you might have missed this is just mentioned. So yeah, there are too many things in this book. So,
Okay. Thank you very much, Yacine.
this is really the Bible.
As I said before, I discovered the subject. Okay.
Okay.
More questions?
Would you please send the slides to who is interested? Do you have an email? What is your
Yeah,
email?
sure. I can, if you have the website, I can put the slides on the website. I can
This
send
is
them.
what we do. Yeah, this is what we
Yeah.
normally do. Yeah.
I will send them to who is the organizer?
Elitza, you can send them to Elitza, to myself.
Okay.
Yeah.
Maybe I can tell you also that Yacine is invited to Institute of Nuclear Research and Nuclear Energy, and he'll be here till end of August. So and you'll have probably many other occasions to meet and talk to him.
Okay. More questions? Comments? So let's thank the speaker again, and I will now stop recording. I will transfer the hosting to the speaker, which is the common practice, because what's left of today's meeting is an informal talk with the speaker, which when face-to-face takes place in a coffee room or something. Yeah. So